Okay, this is the second hour of Physics 1C for March 23rd. Okay, we just derived this result for the drift velocity. This is, again, the rate at which electrons tend to flow inside of a wire. And so I just wanted to talk about what this kind of means. So when you use any type of electrical circuit, like, for example, let's say you switch on your light switch in your home, does it take any time for the light to come on after you turn the switch?
Not really. No.
No, it's really fast, right? Okay. You might even say it's instant. It pretty much is instantaneous. It's not, but it doesn't really matter. As far as you can tell, it seems instantaneous, right? Okay. So how can it be the case then that the drift velocity is so slow if the moment that you turn on your switch, the charges start to flow, basically, through the light bulb or whatever you're talking about, right? Why is that the case?
Must be packed with charges.
What do you mean?
Like, there's not much room for them to like kind of spread out. It's kind of like a full glass of water. Like if you that's like full to the brim. Like if you try to put just like one more drop, then there'll have to be some spillover.
Okay. So you're saying that the whole circuit is basically just filled with little electrons packed in really tightly? Is that what you're saying?
I don't know if I want to use the word tightly packed. I mean, there's enough that
there's 8.45 times 10 to the 28 charges per meter cubed. I think that counts as tightly packed, right?
I don't maybe. But
I mean, it's a bunch, right? It's a bunch of charges per meter cubed.
Yeah, there's a bunch.
Okay.
They definitely feel the influence between each other, though.
They don't feel the influence between each other, but they definitely feel the influence of the battery. So when you close the switch, I mean, they can feel the influence of each other. They got to get really close, though. When you close the switch in a circuit like this, okay, what happens is that even though the charges themselves are moving at an extremely slow rate, so they're just like moving along at probably less than a pixel per second, they're moving extremely slowly through this circuit, right? The charges are. But the thing is that when you throw the switch, the thing that happens is that an electric field gets set up all throughout the circuit. You know, there's an electric field in this part, there's an electric field in this part, there's an electric field in this part here, and the rate at which that electric field gets set up is basically instant. Okay, so even though the charges move very slowly, the entire wire gets subjected to this same electric field almost instantly. So even though the charges move slowly, the electric field is set up almost instantly. And it's set up throughout the entire wire, which makes all of the charges move. And I think that Kenneth maybe said the speed of light. Yeah, the rate at which the electric field gets set up is like that at the speed of light, basically. So the electric field is set up almost instantly. And then all of the charges in the circuit start to move at the same time. All of them at this rate. And that rate of charge flow is enough to basically light up this light bulb, or run your toaster, or run your computer, or whatever it is you're using. So when we have charges that are flowing, even though they're moving really slowly, we can extract a huge amount of energy from them. Right? That's what we use electric current to do, right? We use it to power our devices. We use it to make our lives easier, effectively. And it works basically like that. Just having a few electrons that are moving at this very, very slow speed is enough to do a lot of work for us. These little electrons are like little worker bees that can power anything we want, basically, right? And they move very slowly, but they do a lot of work with that motion. Okay, do you have any questions before we move on to talk about, I think next is resistance?
Now, are we appealing to like just a mathematical model? And we're like, okay, so
Sure. Everything we're doing in this class is a mathematical model. Yeah, I mean, this is a mathematical model. What do you mean by that?
oh, like the electric. I mean, an electron is like a physical uh, matter.
Mm-hmm.
I wouldn't really call that a mathematical model. I
What do you
mean, we
mean?
could use mathematical models too. Like the electric field,
Uh-huh.
like what is that,
What is it?
exactly? Or the nature of it. You're saying like since it, it's set up instantaneously,
Yeah, I mean, so it's not instant. It's an almost instant.
almost.
It's on the order of like 10 to the 9 seconds. Something like 10 to the negative 9 seconds. Like on the order of like a nanosecond. So it's really fast. It's so fast that we can't possibly perceive this with our own eyes. We'd have to have an instrument to measure that. Okay, are you asking like what the electric field is, or I don't understand what you're asking?
Or are we just assuming the nature of like this mathematical model?
Um, which part of it? You talking about the electric field, or
Yeah. I mean,
so?
there's probably experiments, to
So,
like flip the switch. Actually, you measure something pretty much instantaneously.
so the thing about electric fields is that there's really only one thing that resists their development, and that's this thing, epsilon naught. This thing tells you the resistance of space itself to the development of electric fields. And inside of a copper wire, this constant is different, but it's the same concept. You have this constant that tells you the resistance of developing electric fields in certain regions of space or whatever. And other than that, there's nothing really stopping these electric fields from showing up. And because when you have, remember this from when we talked about conductors and electrostatic equilibrium, that if I have a conductor and it has a certain potential, then that same potential is going to be applied all throughout the conductor, basically, right? So, for example, if this is 10 volts and the other side of the battery we define to be 0 volts, that means up until we reach an object like a light bulb or something like that, the entire wire on the right-hand side is at 10 volts. Okay, maybe the part that's right next to the light bulb is at like 9.99 volts, but, basically, this whole piece of wire on the right-hand side is at 10 volts. And it's at 10 volts almost immediately as soon as I close the circuit, right? And because of that, that means there's an electric field within this that kind of tends to point back to the 0 point right here, right? But what part of the mathematical model is bothering you about this?
It's just a vector field.
Yeah, it's a
And
vector field.
mhm.
And that's a mathematical model of what electric field is, that's right. And what about that?
when the switch closes, it's just and okay, so it's just a vector field.
All it really means is that when you close the switch, there's a force placed on charges inside the wire, right?
Mhm.
It's really no different than the following. Suppose that I have a hill, right? And I've got a ball that I place on top of the hill, but I put some type of obstruction right here that makes it so the ball can't slide down the hill, right? If I remove the obstruction, the ball will immediately start moving, right?
True.
That's basically the same idea. The
That's
little
a good.
obstruction is like the same as the switch. You close the switch and now the field is there. Now you could say in the case over here, well, there was already a gravitational field that existed here, right? You could say that if you want to. You'd be like, oh, well, there's already a gravitational field, so of course when you release the switch here, the ball is going to fall down the ramp, right? But you could say the same thing about the battery. Within the battery itself, this is almost, I guess this is not exactly the next thing we're talking about, but we will be talking about this soon. I mean, the battery itself has an electric field as well. And the moment that you connect this, it's just allowed to start using that electric field. In the same way that the moment that you disconnect this little piece right here, the ball is allowed to start interacting with the gravitational field. Now, it was already interacting with it. It was just that it didn't have a path that it could move from here to here. But you open up that path by doing this. And in the case of the switch, you open up the path by closing the switch. That's really all it is. That's going on there, I guess.
That's a good analogy.
Okay. Yeah, I think almost always when you're thinking about what the gravitational field is and what the electric field is, that it's a good idea to just kind of... If you're not understanding electric field, just think about gravitational field, because it's a lot simpler to understand. Because you could physically observe these balls as they move down, whereas we can't really observe the electrons as they move through here. Technically, they'd be moving the other way, but it's really not important. You just need motion. As long as they're moving, they will light the light bulb up. And that's the next thing we want to talk about is, like, what is a light bulb and what makes it glow? And the answer is basically resistance. So that's the next thing we want to talk about here. So we want to talk about resistance and resistivity. Okay, so resistance is a type of, I don't know how else to say it. It's a resistance to electrical flow. It's a resistance to the flow of charges given an electric field, basically. Okay, that's what electrical resistance is. So different types of materials are going to allow charges to flow more easily than others. Okay. And we already know this because there's classes of things such as insulators, and there's things called conductors. And we know that the conductors are better transmitters of not only electricity, but also they're better transmitters of heat, right? If we look at all the things inside of here that are... Is this big enough that you can read the words in here, or should I make this bigger for y'all?
I can read them.
You can read them? Okay. I just don't know if people are on, like, phones or something, they can't read it. So what we have here is basically a table of what we call resistivities. And again, resistivities are a measure of a resistance to electrical flow, a resistance to a given amount of current for an applied voltage. Okay, and yeah, you've got insulators over here, things like amber glass, lucite, mica, which is just rock, quartz, sulfur, Teflon, and wood. Teflon's an insulator? I didn't know that. And then over here on the left, you've got conductors, silver, copper, gold, aluminum, etc. All metals, right? And then a bunch of insulators. Now, I think conduction of heat is probably something we're all more familiar with. So would you all agree that everything that's over here on the conductor side for electricity is also a good conductor of heat? Are metals good conductors of heat?
Yes.
Yeah, if you put a metal pot, like I've got a metal stock pot that I used to cook, and if I put it on the stove and I'm boiling water in it or something like that, it has metal handles. If I touch those metal handles with my hands, they're going to be really hot, right? Because the whole thing's made of metal. But of course, you have certain devices, like I've got a pan that has it's made of metal, but then it has a rubber handle. So that rubber handle insulates my hands from the flow of heat, right? If I'm touching the handle. So we're all very familiar with those ideas. Well, it turns out that the same things that are good conductors of heat also tend to be good conductors of electricity. Does anyone know why that might be the case? Now, I know you all know that metals are good conductors of heat, right? Why would it be the case maybe that the conductivity of something like silver, as far as heat and electricity, is similar? Why is silver a good conductor of heat and electricity? Any ideas?
Well, heat's related to like how fast molecules are moving.
Yep.
So if they're allowed to move freely, they can gain more velocity.
Okay, yeah, so let's back up what you just said real quick, and let's clarify. You're on the right track. So you said heat is a measure of basically how quickly molecules are moving. That's not exactly right. What is the thing that measures how quickly molecules are moving? It's not
velocity.
Heat. Their velocity, right? But what is that connected to? What's the macroscopic?
Distance.
Huh?
Like distance traveled over a certain interval of time.
Yeah, but let's say that I have a...
Friction?
No.
Yeah, I know. It doesn't sound very good.
Look, so
It's
If
a jiggliness.
it's a jiggliness, yeah, but I mean, what's the macroscopic variable that we use to describe how fast molecules are moving?
Kinetic energy.
It's related to kinetic energy, but then the kinetic energy of the molecules. What's the macroscopic variable that we use to describe how fast molecules are moving? I don't mean like exactly how fast they move, but like on average, how much kinetic energy they have, how much energy they have. Maybe you all don't know the answer.
I was gonna
Pretty
say
sure
velocity, but
pretty sure you probably do that.
It's definitely something we learned in Physics 1B.
Yeah, it's from Physics 1B. How do you measure the average kinetic energy of a bunch of molecules of gas?
frequent.
No.
No, that's not what it is.
I think I forgot what it was.
I was gonna say frequency of jiggliness, but
I mean, heat's on the right track. It's just the wrong word because heat's a flow.
No, it's the flow of energy.
Oh, come on. You guys know the answer to
Like
this.
vibration?
I know what you're talking about. It's in my mind.
Just look in the chat.
Or like RMS? Like the.
You're
Oh,
getting
that's
way too
temperature.
complicated. You're getting way too complicated.
Okay.
The answer is Delvino said it's temperature.
Yeah.
Temperature is how we measure the average like kinetic energy of molecules. It's temperature. And there's like a direct connection between temperature and kinetic energy. It's like you take something like 3/2 the Boltzmann constant multiplied by the temperature, and this gives you basically the average kinetic energy of your system. Anyway, that's not important. I wanted to distinguish between heat and temperature. That's what I wanted to do. Okay? So again, I'm going to ask the original question I had. Why is it that things that are good conductors of heat are also good conductors of electricity? What makes something a good conductor of electricity?
Allows charges to flow freely.
Right, there's a bunch of free electrons that they can flow around freely, right? Well, don't you think those charges should also be affected by temperature? They should, right? If they're really hot, they're probably moving more fast on average. They have more kinetic energy on average, right? So it turns out that the flow of heat and the flow of electricity are both related to the exact same thing. They're both related to electrons. The reason why conductors are really good conductors of heat is because the electrons themselves can get really, really hot and they can easily flow through the system. You know what I mean? So if you consider, for example, if you take like a hot poker, a piece of metal or something like that, and you put it into like a campfire, right? So you've got like a campfire here or something like that. If you take a piece of metal and you put one end of the metal close to the thing right here, what's going to happen is that electrons are basically going to start to move up to the other side of the metal. And the flow of those electrons is going to make it so that this end is going to be hot. And even if the other side starts cold, it's eventually going to start heating up as well, right? And it's literally the electrons themselves that carry that energy because they're free to move around. And they're free to conduct that heat, basically, right? So that's the reason why, is because the flow of heat inside of a metal and the flow of heat the flow of electricity inside of a metal are both related to the electrons. That's where it comes from. It's because the electrons can move around so much. And they can also get hot. And then they can transmit their heat back to the front much more quickly than a stick would. Because if you put a piece of stick, like if you put a piece of wood, piece of stick, what am I talking about? If you put a piece of wood in the fire, the wood will combust, right? It'll start burning, right? But this side of the wood will never get hot, really. Or it might after some very long period of time, right? But it would take a long period of time, right? Because the whole thing would literally have to burn. Because the wood doesn't have little free charges that can flow up to the front. The charges, the electrons inside of the wood, the protons inside of the wood, the nuclei, they're all kind of stuck to their individual places. They don't move around very much.
So is the speed of heat a little or near the drift velocity of these electrons?
I don't really know the answer to that question. I think the answer is no. It's not related to drift velocity at all.
Yeah, I would think no.
But
Definitely not instant.
The phrase speed of heat, I'm not familiar with what
I don't know
what that would mean.
Temperature flux.
Yeah, I mean, you could define something as like a temperature gradient. You could come up with something like the rate at which the temperature is flowing. That's certainly something we talk about, but there's no like fixed speed of heat in the same way there's like a fixed speed of light. And remember that the drift velocity is also a function of how much voltage you apply to the system. So you can increase or decrease the drift velocity based on that. So They're not exactly connected to each other. All right, so okay, so resistivity. All right, so resistivity in electricity is the resistance to the flow of electricity. And this equation down here is what we call Ohm's Law. Now, Ohm's Law is something that I can't really derive for you, although I'm going to derive a version of Ohm's Law that we're going to use. Ohm's Law was experimentally determined by a scientist named Ohm. Off the top of my head, I don't remember what his first name is. I was going to guess, but I don't remember what his name is. So Ohm's Law basically relates resistivity, rho, to the ratio of the electric field set up in the wire divided by the current density J. Now, this is not the form of Ohm's Law that we're going to use, but this was basically experimentally determined, or empirically determined, however you want to say it, by this person named Ohm. Okay, so he was able to realize that there is a fixed ratio within metals, within what are often called ohmic conductors, that the size of the electric field divided by the current density within the wire is directly related to the resistivity of the material. Okay, and the resistivity itself you can see is measured in ohms times meters. Okay, this symbol omega, capital Omega, 1 omega, is 1 ohm. So the symbol for resistivity or resistance is named after the scientist Ohm. And 1 ohm is a type of measure of resistance. Now, resistivity is measured in ohms times meters. Resistance is measured in ohms, which is what we're going to get to here in a second. Now, you can see what the values are right here. You can also see, if you look carefully at this, that every single one of them is of the same order of magnitude. Okay? The higher that this number is, okay, the higher the number is, the more resistance there is to the flow of electricity. Okay? Now, all of them are around 10 to the negative 8 ohm meters. All right? But you can see that silver, I think these are in order, right? Yeah. Silver is the best conductor, followed by copper, followed by gold, and then so on and so forth. You can see that lead is nowhere near as good of a conductor as silver, for example. It looks like silver is about almost 20 times better than lead at conducting electricity. This should give you an idea why most of our electrical circuits are made out of these three metals right here: silver, copper, and gold, because they're very good conductors of electricity. All right. What does it mean to be a bad conductor of electricity? Something that's a bad conductor of electricity, things that are lower on this list right here, or things like insulators, they tend to get really hot when you pass electricity through them. Okay? Now, maybe that's what you want. Maybe in certain situations, like if you're making a toaster, maybe your goal is to take electricity and convert it into heat so that you can heat up toast. In that case, you'd want to use something that has the ability to transfer current, but has a high resistivity. So I'll just put over here on the side that high resistivity, or high resistance, means that the conductor will tend to heat up. When current flows through it. And ultimately, this is what we use resistors for. We can use resistors to control currents, but we can also use resistance to just basically convert electricity into heat. Right? That's what we do with a large portion of devices that we use. A light bulb basically takes the flow of electricity through the light bulb that heats up a filament that then gets red hot, and when it's red hot, it creates light. I'm talking about like old incandescent bulbs, not like the more modern like fluorescent bulbs. In the case of a toaster, as I said, or the case of an electric stove, you have a high resistance coil, you pass electricity through it, it glows hot, and then you use it to cook things, right? In a space heater, like a space heater is a type of thing that basically works similar to a toaster. And you can visibly see these things, right? If you look inside of a toaster, when it's turned off, you see these black coils. When you turn the toaster on, the coils glow red hot, right? And what's happening is literally just charges that are flowing through the material are interacting with the material itself, and that produces a type of friction, if you want to think about it that way, that then causes the objects to kind of glow bright, okay? So high resistivity means the conductor will heat up when current flows through it. That's basically what it means. So we want to take this version of Ohm's Law, and we want to connect it to current and voltage, because those are going to be the two things that we use the most frequently. So let's consider that we have a conductor. And let's say that this conductor has a cross-sectional area A that's uniform throughout the conductor. Let's say that it has a length L. Let's say that it is hooked up to a battery. Remember, this is a battery symbol. This is plus, this is minus. And let's say the battery has a potential difference delta V, which means the potential difference between this point and this point is also delta V. It could be like 10 volts, for example, or whatever. As a result of that, there's also going to be an electric field that's set up within this wire. It's going to point this way. I think that's all we need. So, given this setup right here, can anyone tell me, how is the electric field in this wire related to delta V and L?
Delta V divided by L.
That's right. If you take the potential difference and you divide by the length of the wire, this gives you the electric field. Again, this is the equation that I told you all you need to remember, but I'm sure most of you have forgotten. That if I have a uniform electric field, the potential difference is related to the electric field by multiplying by the distance, or the length of the wire in this case. Okay, that's the electric field. That's going to use that. We're going to replace that here for E. The other thing we're going to need to replace is J, but J was current density. It's basically just current, electric current, divided by area, like that. If we take these and we plug it into our equation up here, what we get is this. We're going to get resistivity, rho, is equal to electric field, which is delta V, divided by the length of the wire, all divided by J, which is current, divided by area. And we're going to rearrange some of these symbols right here. So I'm going to multiply the I over A over here, and I'm going to multiply the L over here. So I think what we're going to get is something like this. Oh, whoops. I don't want to change the symbols on you. Okay. So look at the math and tell me if that checks out to y'all. Okay. So what we're going to do is we're going to look at this piece right here, and we're going to define we're going to define resistance, capital R, to be that quantity right there. Resistivity multiplied by the length of the wire, and then we divide by the cross-sectional area of the wire. Okay? This is what we call resistance. So resistivity is a property of the metal itself. Okay? Rho. It's a property of the metal itself. It's something that you look up in a table. And notice that these are resistivities as measured at 20 degrees Celsius. The resistivity actually increases as temperature increases, but we're going to talk about that here in a second. So we're going to define electrical resistance, the resistance to the flow of electricity, to be capital R. Okay? And if we do that, then we get a very nice version of what we call Ohm's Law. This equation then is going to be delta V is equal to current multiplied by resistance. This relates the current flowing in your wire, and in this case there would be some current flowing through here. I left that off. There would be current flowing in this wire here, I. It relates the current flowing to the potential difference between the ends of the wire and the resistance. This is usually what people call Ohm's Law. Technically, I guess, according to your textbook, this is what people call Ohm's Law. But honestly, in like modern textbooks, any type of textbook you look up, this is going to be we're gonna call this Ohm's Law in this class. It's a very, very, very nice, simple relationship. And, we can say some things about what resistance does now pretty clearly. So suppose that I tell you that I have a setup where I've got, let's not use yellow. Let's say that I've got a setup where I take a battery, and I tell you the battery has a voltage of 10 volts, and I connect it up to a resistor. Okay, I'm going to show you what the symbol for a resistor looks like now. It's basically just this, kind of a zigzag, jagged line. We call that a resistor. This thing is what we call a resistor. It's a device that's designed with a specific resistance. And let's say that I tell you that I have a resistor that has a resistance of, let's just use like a simple number, like let's use 500 ohms. So resistance is measured in ohms, this thing. You can actually go to stores and you can buy resistors. They are, I'll show you some pictures of them here in a second. Suppose that I have a system like this. Well, it turns out that I can exactly figure out how much current flows pretty simply in this system, because according to this equation, the current that flows should be equal to the size of the potential difference divided by the resistance. So hopefully this equation helps you to understand what resistance is, because what this says is if, for example, I have a 10-volt battery and I want to know how fast the current is flowing, it's going to depend on how much resistance I have within the circuit. And that amount of resistance in this case is 500 ohms. But I could, in principle, put a bigger thing in there if I want to. And if I do 10 over 500, that's 1 over 50, which is going to be, I think, 0.02. Oops. 0.02 amps. Is that right? Is 10 over 500 equal to 0.02?
Yeah.
Thanks. I'm glad at least one person's listening. So this tells you, if you look at it this way, that the bigger the value of the resistance, right, what happens to the current? If I were to double the resistance right here, what would the current be?
0.01.
It would be half.
It'd be half, right? Okay. So that's why we say resistance is like this measurement of the kind of resistance to flow of current. The bigger the resistance, the smaller the current's going to be. You can, of course, increase the delta V, and that'll give you more current. Now, if you think about it this way, then delta V is a type of force, in a way, that kind of, we call it an electromotive force, that tends to move charges throughout the circuit. And the rate at which those charges move is going to be dependent upon how much resistance there is to flow. And then the rate at which they flow is just given by the current itself. There's effectively like an equivalent version of this equation in Physics 1A. And the version of that is basically that the relationship between the drag force, here I'll write it like this, the drag force is equal to some constant that sometimes we use B for, multiplied by the velocity of an object. This is kind of the Physics 1A version of Ohm's Law. Okay? Drag force is related to something that we call the drag coefficient, which is effectively like resistance. But then it also depends on how fast the object moves. Right? The faster the object moves, the more the drag force you're going to get, right? So this is kind of it's kind of a good analogy, but it kind of fails because drag is kind of weird because it can't actually provide propulsion. So we're going to see a better version of this here in a second, but the drag coefficient is like resistance and the velocity is like current. And then delta V is basically like a force. We're going to have a better version of this equation here in a second. All right, let's go back and talk about this right here. So we said that electrical resistance is basically given by rho L over A. This tells you how you can construct something that's called a resistor. Let me show you some pictures of resistors real quick. If you ever looked at the inside of a toaster, you've seen a resistor effectively. So commercially available resistors kind of tend to look like this. They are... where's one that will show me what they actually look like inside? Hold this is what they look like. You can go to like a, I was gonna say Radio Shack. Are Radio Shacks still around? I don't really know. This is one getting really hot. I wonder if we can find one that you can actually see inside of it. What if we search for, it's gonna give us an actual picture of one. Okay, here we go. Kind of. This is better. Here we go. There we go. This is what I want. So you have a wire that comes in this side. You have a wire that goes out this side. There's an external coating that's ceramic or something that's that tends to be a pretty good resistor, right? And then you basically have wire that's round around this, right here. And that's what your resistor is. It's quite literally just a bunch of wire that's been wound around like this. And the reason why it's constructed like this, we can understand if we, here, can I?
Oh, the length.
The length, exactly. Let's see if we can just copy this picture into our document here so we can look at our equation here. So our equation says that resistance, right, is a function of, and Cam already figured it out, the resistivity, which again, this is just a number that you look up in a table, okay? Maybe it's 10 to the negative 8, multiplied by the length of the wire, and then you divide by the cross-sectional area of the wire. That means that if I want to make a resistor that has a lot of resistance, the simplest way to do it is to have a small cross-sectional area, right? Tiny little area, and I don't mean the area of the end cap, I mean the area of the wire itself that's inside of here. And I also want to have a long wire. So you want to have a skinny wire that is really long, and one way to make that so that it's not just a really, 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 really long wire is to just take the wire and just wind it around something, right? And that'll give you what we call a resistor, right? So yeah, we're gonna do a calculation of an example of this, but that's kind of the idea. It's literally just a long wire. Now this also means that any piece of wire that I have necessarily has resistance to it, right? Any piece of copper wire that I have automatically has resistance to it. I want to look at just this equation too, and I want to see if it makes sense to you.
Professor,
Yeah, what's up?
does it also mean that it's always going to be hot, resistors?
They're only hot when current passes through them.
Okay.
Only when current passes through them. Now, how hot they are is going to depend on how much current you flow through them. You know what I mean?
Yeah.
So if you try to flow too much current through a system, that more current than it can really handle, then the resistors themselves will start to burn. They'll literally just catch fire. You know what I mean?
Okay. Yeah.
So that you don't want to have stuff like that happen. Now, in our homes, we have either fuses or circuit breakers to prevent that from happening, right? So if too much current flows through your home system, your home electrical system, then the breaker will trip, right? Have you all experienced that before? You all know what I'm talking about? And all the devices in your house will just lose electricity, and you need to go and basically turn it back on. And it's designed like this because if you put too much load on your system by, for example, running your washing machine and your dryer while you're using your microwave and you're also using your electric stove at the same time that you're blasting music through a gigantic amplifier and maybe you're also playing the guitar or something like that. If you have a lot of things running at exactly the same time in your circuit, you may overload the circuit and it may try to draw too much current, and when it tries to draw too much current, there's a limit. And when that limit is reached, like let's say it's 10 amps or something like that, I think it's much smaller than that. Then 10 amps is a lot of current. Then basically just like the system shuts off. And we also have electrical devices that have fuses inside of them so that the device itself, if too much current flows through it, the fuse will burst and it'll prevent the object from basically either overheating or malfunctioning or whatever, causing damage internally to it. Right? Good question. Okay, let's look at this equation and see if it makes any sense. This tells us that the resistance to electrical flow depends on the length of the wire and the cross-sectional area of the wire, right? Does it make sense that the resistance to electrical flow should depend on how long the wire is? Does that make sense? That is to say that a 10-meter wire of copper compared to a 1-meter wire of copper would have 10 times as much resistance to the flow of current. Does that make sense?
Yeah, because the charges have to travel over a longer distance. They can't.
Yep, and they will inevitably, as traveling over that longer distance, it increases the probability that they're going to interact with some portion of the material. That's really what the resistance comes from, is from the material itself and from the resistance to the charges from trying to basically do this. They're trying to get through the material. And actually, here is where we can go back to we can actually go to the simulation and understand better what's going on here. Because what's going on in this picture is, let's move it down to 0 volts. We've got our resistor up at the top. I don't think I can get to 0. There it is. We've got our resistor up here, and it has all of these little pieces to it, which is basically nuclei. This is the material itself. These little green things, and they're jiggling a little bit because atoms never really truly sit still. Oh, the resistance is maximized here. Let's reduce the resistance. All right. So, oh, we can show inside the battery. I don't know if we want to do that or not. Okay, so these charges, they try to flow through here. And when they do, let's make a move by putting some voltage on here. So increase the voltage up to like 5 volts or so. So now we've got charges, and they're trying to flow through this system. But as they flow, they inevitably interact with the material. So the longer it is, the more material there is, and the more things that these electrons are going to have to work their way through to get to the other side. Now you can see the effect of this is that there's a current flowing here. What's going to happen to the current if I reduce the resistance?
Go faster.
It should go faster, right? Let's see if that's the case. So we reduce the resistance here. And boom, you can instantly see that these charges are moving way faster through here. And you can also see the current went up. Well, I'll just watch this device right here as I increase this. So I'm going to increase the resistance. The current should go down, and it is. The other way that I could increase the current is by increasing the voltage, right? If I ramp up the voltage here, the current will go way up. And the other thing you see here is that the temperature of our resistor has now started to increase. We can make it even hotter if we make it have more resistance. Well, not exactly, because notice that while the charges are impeded more, the current also went down, right? So there's kind of a delicate play-it balance here, like that. The temperature actually goes up when I reduce the resistance, because now the current goes up. And I believe the temperature is related to the current squared. So you really want the current to be as big as possible. The bigger the current gets, the hotter this object gets. It's also related to resistance, but... Okay.
Are resistors used for current control?
Yeah, absolutely. Absolutely, yeah.
So are like the
Just like a valve in a... well, not exactly, but keep going.
So are sources of sources like potential sources?
Mm-hmm.
Is there the current that they output? Is that hard to kind of just build into itself? Since from
Well,
okay,
it's not about the
source of potential.
For a source of potential, it's not about the current that they output. It's about how much voltage is there, right? How much energy is there, right? They don't output a fixed amount of current. The amount of current that they output is dependent upon what you hook them up to, right? It's dependent upon this.
So like electronic devices don't blow up.
Mm-hmm. Yeah. Okay, so we talked about. Let's go back to what we were trying to do. Resistance is equal to rho L over A. The longer that L is, oh my god, it's already 4:06 p.m. The longer that L is, the bigger the resistance is going to be, because there's just more material, right? What about the denominator, the area? This says basically that the smaller that the area is, the bigger the resistance is going to be. Does that make sense?
Mm-hmm.
If you have a really skinny wire, it's going to be much harder for the electrons to squeeze through it. The extreme example of this is an incandescent light bulb. Inside of an incandescent light bulb, you have these little filaments. You guys know what I'm talking about when I say filament? If you look inside of a light bulb, you're going to have, your light bulb. It's like this. It's got the casing down here that you connect into the socket, right? But then inside there's this really, really, really tiny filament, and the filament is constructed like this. It has the same kind of nature of those resistors that we looked at. And so imagine that you're an electron, and you're sitting right here, and you're trying to go through here. the electron has to squeeze its way through all these little curly cues or whatever to get all the way through here. And as a result, the electron is going to interact with the material, and that's going to cause energy to dissipate. This thing will heat up, and when it gets red hot, it will basically start emitting light, right? So the skinnier the wire is, the bigger the resistance is. Let's do this resistance calculation, and then we'll take a break. All right, so this says electric field potential difference in resistance in a wire. We have an 18-gauge copper wire. It has a cross-sectional area of 8.2 times 10 to the negative 7 meters squared. It carries a current of 1.67 amps. Let's write this stuff down. The area is 8.2 times 10 to the minus 7. The current is 1.67 amps. We want to find the electric field magnitude in the wire, the potential difference between two plates of the wire that are 50 meters apart. So our wire now we know is 50 meters. The potential difference between those 2 points and the resistance of a 50-meter length of this wire. We also know that it's copper. So one of the other things we can look up in a table is what the resistivity of copper is. And it's, as we saw before, it was something times 10 to the negative 8. And that unit is ohms times meters. .72. Okay, and then we're also going to need Ohm's Law, which is rho equal to E over J. So I'll write that one down here too. Okay, the first thing we want to do is to calculate the electric field magnitude in the wire. We can use this equation because we also know that the current density is equal to the current divided by the area of the wire. So combining all these equations together, we should be able to find the electric field. So the electric field should be equal to the resistivity times J, according to that equation. So it's going to be equal to resistivity, which is 1.72 multiplied by J, and J is going to be I over A. I is 1.67 divided by A. I left my calculator in my room. Can you all calculate this for me? As soon as you put an answer in the chat, I'll put it right here. Part B says the potential difference between 2 points in the wire 50 meters apart. Well, for that, we can just say delta V is equal to the electric field multiplied by the length. So whatever we get from this answer over here, we're going to multiply by the length, which is 50 meters. Okay, DeHal got 0.03. I want to wait just to finish. Let's see what Jacqueline gets. Okay, you guys got the same answer. That's great.
Yeah, same answer.
That's great. Okay, so you get 3.5 times 10 to the negative 2. We'll use volts per meter, because that's the one that's going to work out the best for the next part. We take that number, so that's the electric field in the wire. And then we do that, 3.5 times 10 to the negative 2 volts per meter, and we multiply by meters. So we're going to get delta V is going to be equal to, let's see, 5 times 35 is like 5 times 7 times 5, so 25 times 7, which would be 175. And then we need to multiply by, so is this what it is? Let you all tell me.
Yes.
Is that right?
Yeah.
Okay. And then part C says the resistance of a 50-meter length of this wire. So if I want to find the resistance, for this one we're going to use oops, go down a little bit. We're going to use resistance is equal to rho times L over A. Rho is 1.72 times 10 to the negative 8 ohm meters. Right there. We multiply by the length of the wire. I'm sorry for changing symbols on you here. I'm just so used to writing it with that capital L. I don't know. Times the length, which is 50 meters. And then we just divide that by the area. Right there. Not 8.27, 8.2 times 10 to the negative 7 meters squared. And we should have meters squared in the numerator, meters squared in the denominator, which means our answer is going to be in ohms, which is what we want. So the resistance of 50 meters of this wire, 50 meters is, after all, a very long distance. Let's see, -8, -7. I'll let you all calculate this. There's no way I can do this in my head.
1.05.
Maybe I could have. 1.05, is that the answer, just ohms? There's no, nothing else? Okay. Now, this is actually a nice, interesting answer. This is copper, by the way. So even though we have 50 meters of this wire, it still only has a resistance of about 1.05 ohms. That's not very much. That's not very much at all. That's a good thing because, you know, the way we use electricity in every part of the world is that we transport electricity from like a power station, a power plant, to people's homes, right? And usually the power plant is not super close to your home. So in transporting that energy, it's nice that we can send it along wires that have very low resistance, because otherwise some of the energy of that electricity actually gets lost as it passes along the wire in the form of heat, because the wire itself is going to heat up, right? And just like in all other forms of physics, you never get anything for free. Energy is conserved, right? So let's say that I start with 10,000 joules of energy at my electric plant, and I want to transport that energy via electricity to your home. Well, depending on how much copper wire there is between the plant and your home, some of that energy is just going to get lost. There's nothing you can really do about it, you know? It just happens because you're transporting along wires. Those wires are going to heat up, and that's going to show up as a loss of energy in that transfer process. But you're not going to lose that much because the resistance is super small. As we'll see in a lot of the problems you're going to do, you're going to be looking at resistors that have resistances of like 500 ohms, 15,000 ohms, stuff like that. So yeah. Okay, that is a good place to stop. We're going to take a 6-minute break. We could take a longer break. I guess it doesn't really matter. It just feels really weird taking a break till like 4:25. I don't know. It's fine, I guess. It's all the same. We had 10 minutes before class where we didn't really do anything. All right, so we're going to take a break. We'll go 4:24. We'll get started again. Does anyone have any questions before we do that, though?
Professor?
Yeah, what's up?
Do you mind posting the notes for the last few classes, please?
Yeah, I'll do that after class today, for sure. I'm
All right, thank you.
kind of behind on that because I've been having some issues with OneNote, but for some reason sometimes it won't let me print, and I was trying last week and just wasn't working. But I'll get it fixed today after class, and I'll definitely get them uploaded for you.
Thank you. Appreciate it.
No problem. All right, so we need to take a break, so we're gonna stop the